So we see that the next couple of sections we're looking at are merged and out of order. So we have 10.7 and 10.5. First off, the reason that we leave out 10.6 is because it's kind of going to be something that we're going to come back to. It's a little different from 10.5 and 7. They kind of mesh better. So we're going to be talking about 4 different tests here: ratio, root, and there's going to be 2 comparison tests. And we put them together in a single section just because this way we have kind of a catalog of tests we can choose from. The reason that we're doing 10.7 and then 10.5 is simply because the ratio and root tests are going to be more of a first choice than the comparison tests. So we'll have ratio and root will kind of be our first line of defense if we've already looked and seen it's not geometric, telescoping, or a p-series. We'll go ahead and apply ratio or root. If those don't work, we'll start looking at comparison tests. If that doesn't work, then we'll look at integral tests. So again, these tests determine whether a series converges, but do not establish the value. So that's our question here, is whether a series converges or diverges. So the first test that we look at is the ratio test. So it says the integral test is powerful but limited because it requires valuing integrals. And so whenever we have something with a factorial, this exclamation point, remember that just to establish what that means for us, the factorial, if we have k factorial here, we're looking at k times the number that came before it, times the number that came before that, all the way down to times 2 times 1. So it's relatively simple conceptually, but in a integral situation, that's not something that we can actually do. And so the factorials are going to pretty much instantly disqualify anything that we see in there from the integral test, which is good because our integral test is long and kind of arduous. So we want to have some way of comparing maybe the terms of a series that has factorials. Remember that guaranteed to get to this ratio test step, we've already established that the limit of our a sub k's as k tends to infinity needs to be 0, right? The divergence test first off. We have to establish this first. If that's not true, this series automatically diverges. So the idea is these terms have to shrink to 0, but does it diverge or converge? We have to determine how quickly do these guys shrink to 0. If they don't shrink to 0 fast enough, we'll diverge. If they do, we'll converge. So what we'll do is we'll compare one term to the term next to it. So we'll make a ratio of the later term over the term that comes before it. So we're kind of comparing each term to the one after it. And we're making a ratio or a fraction. We're going to let our k, our index, go to infinity. We're going to look at what happens sort of on the tail of this. And we're going to let that equal r. Not to be confused with, this is not the r from the geometric series. And that's something that we're going to have to be very confident with, that these are different. Remember the properties of r we're looking for in a geometric series. It is going to be different from what we look for in the ratio test. So we take this ratio, let k go to infinity, that's r, and we look at values of r. So if r is between 0 and 1, including 0, this series converges. Right, so that's the same as the geometric series. And if r is greater than 1, including infinity, the series diverges. That's also same. But on number 3, if r equals 1, the test is inconclusive. For geometric series, looking at r as just that common ratio, that is going to be, if r is equal to 1, divergent. In the ratio test, that means the test is inconclusive. And in this class, I'm not really going to give you a lot of trick questions. This likely just means wrong test. You shouldn't use the ratio test on this one if you get r equals 1. That means you needed to use something else. As it says here, ratio test says the limit of the ratio of successive terms must be less than 1 for convergence. Often we'll see both this test and the root test that comes up written with absolute values. And in that case, we have to have positive terms. We are going to be, oops, that's a typo there. Remember that for 10.5, 10.7, all the stuff we've worked with so far, we're working with only positive values. In 10.6, that's the reason it's kind of set off by itself. We're actually going to look at stuff that's got negatives too. All right. So we've established what the factorial means. One extra thing to remember is that 0 factorial is equal to 1, right? So 2 factorial is 2 times 1. So 1 factorial is just 1, right? You get that by dividing by 2. So you can write that 1 factorial is 2 factorial over 2. That's 2 over 2, which is 1. So defining 0 factorial is going to be, we define 0 factorial as 1 factorial divided by 1. So we get 1 over 1, which is 1. So that's just the definition of 0 factorial. So it is something we're going to have to remember. So we'll go ahead and use the ratio test to figure out the convergence of this series. So what we want to do is we want to set r equal to the limit as k tends to infinity of 10 to the k plus 1 over k plus 1 factorial. We replace both of our k's with k plus 1s. When we replace it in a factorial, you need to make sure that you use parentheses on that. And then we'll have 10 to the k over k factorial. It is important that we have the limit there. Otherwise, there's really, this isn't the ratio test. So we've got this set up, and now we need to simplify and figure out what r is actually equal to. So the first thing we probably want to do is get rid of this whole compound fraction deal. So we'll keep the limit here, limit as k tends to infinity, right? And we flip and multiply. So we've got 10 to the k plus 1 times k factorial over k plus 1 factorial times 10 to the k. And just as a side note, we already know that factorials grow faster than exponentials here. So in your head, if you do the divergence test, this should go to 0. So we are good to use this series after all, or use this test after all. All right. So now we need to simplify this in some way. Well, we know that 10 to the k plus 1 can be split into 10 to the k times 10 to the 1. So we'll have some cancellation that happens there. But what do we do with k plus 1 factorial? Standard trick, k plus 1 factorial is k plus 1 times k minus 1 times k minus 2 times ... all the way down to 2 times 1. Everything past the k plus 1, this is k factorial. So our standard trick for a factorial is to sort of split off our first little bit here and leave the rest as a factorial. When we do that, we now have cancellation of the factorials, cancellation of the 10 to the k's, and we are looking at the limit as k tends to infinity of 10 over k plus 1. Take the limit, we get 0. Therefore, and we could just start writing out what the series is. K equals 1 to infinity of 10 to the k over k factorial converges by the ratio test. And that would be our answer. State the series, state what it does, and state which test we used. That is the standard practice for everything other than telescoping and geometric. All right, so now we have kind of our standard practice, and we can see where the ratio test is kind of the most useful. It's very useful with exponentials because we can split our exponential. It's very useful with factorials because we can split our factorials. So it's going to be our standard practice when we see nothing but factorials and exponentials to use the ratio test. So first off, we do notice we have a factorial over an exponential. The divergence test will say that this guy should actually diverge. But we'll pretend that we don't remember our growth rates for these kind of less standard functions. So this is infinity by growth rates. There's also not a lot of work to show if we do it this way. So we'll go ahead and do the ratio test, pretend we don't know that. So that's the limit as k tends to infinity. The later term, so we plug in k plus 1 over the earlier term, k factorial over e to the k. So we'll get the limit as k tends to infinity, we'll flip the fraction first. Sorry, flip the denominator there and multiply it in. So we have e to the k here over e to the k plus 1 times k factorial. So we have the limit as k tends to infinity of, we split the k factorial, k plus 1 factorial again. We also split in the denominator the e to the k and the e to the k, e to the k and the e to the first. All right, so the e to the k's cancel, the k factorials cancel, and we get the limit as k tends to infinity of k plus 1 over e, which goes to infinity. Therefore, our sum from k equals 1 to infinity of k factorial over e to the k diverges by the ratio test. And I should be able to look back in your work and see what your R value was, and of course see how you got it. But I should be able to, it should be obviously there, kind of the last thing you've done. So make sure that it's visible in your work. Of course, I do need to see getting R, the entire process. All right. Similar kind of thing here. We could actually take a look at the growth rates and just remember that, but we'll go ahead and use the ratio test. Another thing to note is that it is what the instructions ordered here. So we'll look at the limit as k tends to infinity. And in this one, we've got k in the base here, as well as in the exponent. All right, and then we have to do that in the factorial as well, and then we'll also have our sort of kth term in the bottom. So we'll go ahead and continue on here, flip, and we'll see what we can do with this guy. We've got k factorial over k plus 1 factorial, k to the k. All right, so one thing we can do is we can still split our exponential here a little bit. So if we pull out one of these k plus 1s, we still have k plus 1 to the k left over. And then in the bottom, we can split off that k plus 1 and the k factorial as well. And so the k plus 1s cancel, the k factorials cancel. And so we're left with the limit as k tends to infinity of k plus 1 to the k over k to the k. And we need to figure out what this eventually is equal to. So this is a bit of a tricky limit to figure out. We definitely have an indeterminate form, infinity over infinity. But this isn't something that we can really differentiate very easily. One thing that we can kind of work with here is we have a k in both sort of exponents. So we can actually pull it out of the fraction here and turn it into this expression. And now that it's sort of applied to our entire limit argument, we can go ahead and let y equal k plus 1 over k to the k and use our natural logarithm argument to kind of work our way through here. So we'll go ahead and set up natural log of y is the natural log of k plus 1 over k to the k. And so using our logarithm laws, we've got k natural log of k plus 1 over k. So we pull that exponent out. So after we pull that exponent out, we're going to go ahead and set this up with a limit. We'll go ahead and take the limit as k tends to infinity of our natural log of y, and that sets up the limit on the other side as well. And looking at this guy, we have an indeterminate form. If we have k go to infinity on the inside here, we get 1. Natural log of 1 is 0 times infinity. So that is the indeterminate form, 0 times infinity. We'll have to send this k to the denominator. And now looking at this, I'm going to have to use L'Hopital's rule. And when I look at the natural log there, I see that I'm going to have to do a chain rule with a quotient rule, which looks unpleasant. So let's see what else I can do. I have a fraction here where the top has addition. I can actually split this up into two different fractions. So I'm left with the limit as k tends to infinity of natural log of 1 plus, I can actually make 1 over k look like k to the negative first, which is advantageous because I have k to the negative first in the denominator. That way I'm being consistent there. So I'll use L'Hopital's rule. For the natural log, I put the argument in the denominator and the derivative of the argument in the numerator. And in the bottom there, I'll just take the derivative. So that's L'Hopital's rule. We'll go ahead and clean up here. I can go ahead and, since I'm dividing by negative k to the negative second, that's the same as multiplying by 1 over negative k to the negative second. And so I got some nice cancellation that happens here. The negative k to the negative seconds cancel. I end up with a limit as k tends to infinity of 1 over 1 plus k to the negative first, which is 1 over k. That guy goes to 0. I'm left with just 1. All right, so the limit of the natural log of y as k tends to infinity is 1. So if I'm looking for the limit as k tends to infinity of y, that's going to be e to the first, which is just e. And so that's what I'm going to have up here. And this guy is greater than 1. Therefore, r here is going to be greater than 1. And so the series k to the k over k factorial diverges by ratio test. Right, we're going to put less and less emphasis on the actual index and all that kind of stuff. Right, like we mentioned previously, the initial index dictates the value of the series, but if we only care if it converges or diverges, then often we can kind of just know that all of our series are going to go to infinity and not really care about the front index that much, but we'll get to that later. So we'll go ahead and, again, just real quick, kind of examine it, see what's happening with the divergence test. It looks like we've got a bit too much in the numerator for this to work, but we'll go ahead and, again, use the ratio test just as it is commanded by the instructions. So we'll take the limit as k tends to infinity, and we'll have to plug in k plus 1 into all of these spots here. We'll go ahead and do 2 to the k plus 1 times k plus 1, and then we have k plus 1 factorial, and then the denominator 3 to the k plus 1 factorial, and then the bottom we have our kth term, 2 to the k plus 1 factorial, 3 to the k factorial. So we have quite a bit of terms to write down here, but the idea is the same. We'll go ahead and write all of the terms from this top numerator here, and we'll go ahead and add this up too. We've got k plus 2 factorial over 3 to the k plus 1 factorial. And we'll go ahead and write the stuff from the denominator of the bottom fraction in the numerator here. Write the numerator of the bottom fraction in the denominator. All right. So let's see what we got. We end up with, we'll go ahead and start splitting up our k plus 1s here. We've got 2 to the k times 2, k plus 1, k plus 2 times k plus 1 factorial. All right, we split the first one off. 3 to the k factorial. In the denominator here, we've got 3 to the k times 3, k plus 1 times k factorial, 2 to the k, and it looks like another k plus 1 factorial. So the reason I didn't split this last one is because I see that I still have a k plus 1 factorial up here. So those will cancel now. One of these k factorials will as well. 2 to the k will. 3 to the k will. And our k plus 1s will. So we get the limit as k tends to infinity. We've got 2 times k plus 2 over 3k. So we've got the limit as k tends to infinity of 2k plus 4 over 3k, multiplied by 1 over k. Oops, that's a 4. So we've got the limit as k tends to infinity of 2 plus 4 over k over 3. This guy goes to 0. We get 2/3. That's less than 1. So actually, just sort of looking with the divergence test wasn't really enough to show that these factorials will still kind of work with the k and end up being really the same, since we have the same number of factorials and the k is not really going to add that much, supposedly. We'll end up with a converging series here. So therefore, k equals 1 to infinity. We've got 2 to the k plus 1 factorial over 3 to the k factorial converges by ratio test. All right, so we see ratio test is best for exponentials, factorials, and k to the first power. So now we'll move on to another test, a very similar test to the root test. It says occasionally a series arises for which none of the preceding tests give a conclusive result. In these situations, the root test may be the tool that is needed. So it's going to be a very similar kind of concept to the ratio test. We're going to start with our infinite series, non-negative terms. Instead of r, we're going to use rho. This is the Greek letter rho. And so what we're going to do is we're just going to take the kth root of our kth term and let k go to infinity. And so we've got similar sort of properties between rho and r from the ratio test. So if rho is less than 1, greater than 0, we got the series converges. Also equal to 0, the series converges. If rho is greater than 1, series diverges. If rho is equal to 1, we use the wrong test. And so we can see this is a pretty situational test. It is very useful if we have a kth power over everything. If we have a kth power over everything, right, you can see that when we apply the limit and the root, we'll go ahead and end up with some nice cancellation. So we've got the kth root and kth power. They will cancel. And so we get the limit as k tends to infinity of 4k squared minus 3 over 7k squared plus 6. Go ahead and multiply by the 1 over the greatest power of k in the denominator, which is squared in this case. And so we get 4 minus 3 over k squared over 7 plus 6 over k squared. These guys go to 0. And so we get 4 over 7, which is less than 1. Therefore, our series here, 4k squared minus 3, 7k squared plus 6, all to the k power, converges by root test. So we can already see where the root test kind of shines. It's going to be where we have a kth power, especially. But we'll see kind of some more spaces. We'll see kind of some more spaces where that happens. It says use the root test. We have a kth power here, and we have k to a power that's higher than 1. That's going to be another place that it happens. When we have a kth power on the outside of our term, or if we have a mixture of exponentials and single terms of polynomials where the power is higher than 1. We'll go ahead and use the root test there as well. So we have the limit as k tends to infinity, kth root, to the k over k to the 10th. And so when we go ahead and apply the root to both the numerator and the denominator, we get 2 over k to the 10th with a kth root on it. So you get the limit as k tends to infinity of, we write this root as a rational exponent, 1 over k. This gives us limit as k tends to infinity of 2 over k to the 10 over k. So here's something that's typically going to happen when we are using the root test on something that's got just a k to a power on it. We're going to have to figure out what this is equal to. And so we let y equal k to the 10 over k. Take the natural log of y, that's the natural log of k to the 10 over k. And so we get 10 natural log of k over k. If we pull this power out front, this should be a k. Pull the power out front, this is what we get. So we take the limit as k tends to infinity of the natural log of y. That's the limit as k tends to infinity of our newfound fraction here. Infinity over infinity, this is L'Hopital's already. When we do that, we get a 1 on the bottom. 10 times 1 over k. So we get the limit as k tends to infinity of 10 over k. This guy will go to 0. So the limit as k tends to infinity of y will be e to the 0, which is 1. All right, so we take that limit and we apply it back up here. So we can, using our limit laws, apply it to both the numerator and denominator. We get 2 over 1, which is 2, greater than 1. Therefore, the series diverges by root test. We say what the series is. So therefore, k equals 1 to infinity of 2 to the k over k to the 10th diverges by root test. All right. So the next one we see here, we have a k on the outside there, a kth power, which means that the root test will cancel that out nicely, and it'll be good. But we do have a subtraction on the inside. We do want to make sure, just real quick, we want to check to see that this is always positive. So we'll compare, first off, each fraction should be positive because we're using positive k's. So we have both denominators are positive for all natural numbers k. And now we'll compare them. K is less than k squared as well. And that's for all natural numbers k. All right, so if we divide on both sides by k squared and then by k, we get 1 over k squared is less than 1 over k. And so if that's true, then we can go ahead and subtract 1 over k squared from both sides. And so that means that our terms are always going to be positive. 0 is less than our guys here. So that means we can go ahead and use rho here. Since it's our first time having a subtraction there, I just wanted to check that, right? So we got the kth root of 1 minus k, 1 over 1 over k minus 1 over k squared to the k. Those cancel. We get the limit as k tends to infinity of 1 over k minus 1 over k squared. Both of these guys end up as 0. We get 0. That's less than 1. Therefore, our series here, k equals 1 to infinity of 1 over k minus 1 over k squared, converges by root test. All right. So we got one more here. We'll go ahead and take a look at this guy in the bottom here. We got that kind of split up exponent. Not really too much point in having it like that. So let's go ahead and multiply those exponents together. And now that I'm looking at it, I kind of have k's involved in both of my exponents. So why don't we actually split that back up? But split it up in the other direction. So if we split it up again, we've got 2 to the 2 to the k. This is 4, so we can go ahead and write that as 4. And since we have a kth power in both spots here, we can actually make this to the k, just like that. And we can already see by divergence test that this is going to fail. So we're going to have divergence. But we were told to use the root test, so we'll just do it anyway. So we have the limit as k tends to infinity of the kth root of k factorial over 4 to the k. So we get the limit as k tends to infinity of k factorial over 4. And that definitely goes to infinity, which is surely greater than 1. And therefore, the series here, we've got 2 to the k squared diverges by root test. All right, so that's the ratio and the root test. And in just a sec here, we'll start looking at our comparison test as well. But this is 10.7, so we'll go ahead and look at 10.5 next here.